Hello, welcome to this introduction to Fermilab. I'm Don Lincoln, senior scientist and frequent host of Fermilab's YouTube channel. Fermilab is America's flagship particle physics laboratory and one of the premier research institutions in the world. It's located just west of Chicago. Fermilab has been in existence for over half a century and has been in the vanguard of our understanding of the universe for that entire time. A theory called the Standard Model represents our best understanding of the subatomic world. Using 12 particles, 4 forces, and an energy field that gives mass to those particles, we can explain all of the matter we've observed so far. 3 of those particles were discovered at Fermilab, specifically the bottom quark in 1977, the top quark in 1995, and the tau neutrino in 2000. And Fermilab scientists played a prominent role in the 2012 discovery of the Higgs boson, discovered at CERN, our sister laboratory in Europe. The Higgs boson is a consequence of that energy field that gives mass to particles. We've also played important roles in our scientific understanding of dark matter and dark energy, 2 substances that are thought to make up a staggering 95% of the matter and energy of the universe. We're still learning about both of them. But Fermilab is not the elite institution that it is solely on the basis of past accomplishments. For now and for the foreseeable future, it is the world's premier facility for the study of subatomic particles called neutrinos, subatomic ghosts that can pass through the entire Earth, with most of them not interacting in their passage. However, a tiny few can interact in our detectors, revealing their secrets. Neutrinos have surprised us many times since they were first proposed in 1930. They interact so little that it took us a quarter century to prove they exist. We were surprised to find that 3 variants exist when we thought that there was only 1. They really shocked us, however, when it was found they could change their identity as if a cat could change into a jaguar, then into a tiger before changing back into a cat again. And we now think that it might be possible that this identity swapping behavior will tell us something about why the universe is made only of matter, when the theory says we should see equal amounts of matter and antimatter. The experiment that will explore this idea is called the Deep Underground Neutrino Experiment, or DUNE for short. Our leadership in neutrino research originates in our outstanding accelerator facility. Using a series of 4 distinct accelerators, we bring protons to higher and higher energy until they are ready to be smashed into targets and converted to neutrinos. And as impressive as our accelerator facility is, we're not resting on our laurels. We're making it even better, faster, and more powerful with an upgrade effort with the unwieldy name of Proton Improvement Plan, or PIP. PIP 1 has been completed, PIP 2 is underway, and there's even a plan for PIP 3 for the future. You'll be hearing more about PIP 2 later in this video. Actually, you'll be hearing about a lot of ongoing and future projects. In fact, I've probably already spoken too much. The rest of this video, you'll hear from our experts, people who are making Fermilab's future a reality. So sit back, listen to what we're doing, and enjoy a series of stories describing one of the most exciting scientific programs on the planet. It's all very mind-blowing.
Welcome to everyone. My name is Anne Mary Teichert, and I work at Fermilab in the Education Office. You are looking at the atrium of Wilson Hall, the big building that you saw behind Don Lincoln during his presentation. This is the main office building on our campus, and it's the building where we would welcome you if you came for a visit. Wilson Hall is named after the first director of Fermilab, Robert Rathbun Wilson. You're going to hear more about the history of the lab from our next speaker. But for now, let's look around the atrium to see what you'd notice if you were here on a visit. In the front corner, next to the doors, is the office of the director and deputy director of the lab. Fermilab is managed by a group called Fermi Research Alliance for the U.S. Department of Energy's Office of Science. The director and his staff supervise the scientific and technical work that's done here, and they oversee the functioning of the lab site. Fermilab is big, with 6,800 acres of land altogether. There are buildings for the accelerators and scientific work, but the lab is also home to over 1,000 acres of tallgrass prairie, and it's been designated a National Environmental Research Park for the many ecosystems on the site. Now let's walk past the elevators and the stairs and go to the Rock West control room. If you look beneath the stairs, you can see through a window into that control room from where most of Fermilab's experiments are controlled. Scientists are at work there monitoring screens that show the status of the experiments. You'll see into this room in a later presentation. Next to the control room is a smallish auditorium. There's a large auditorium downstairs, and there are conference rooms scattered all around the lab. These rooms are always busy locations for staff meetings, scientific presentations, colloquia, conferences, and collaboration meetings. The type of science done at Fermilab is highly collaborative. Coming back to the front of the atrium, you can see a little garden with live plants. The garden is here because Wilson wanted to bring nature from the outside into the lab to beautify the workplace. Behind the garden is our cafeteria, and you can have lunch there with the staff if you come on a visit. Just upstairs from the cafeteria is Fermilab's art gallery. Fermilab has a proud tradition of hosting fine arts displays, and a few years ago we started an Artists in Residence program for visual artists. The gallery is also the gathering place at 3:30 on workday afternoons, when all the staff is invited in for coffee and cookies. On the same level as the art gallery, you can see a display of flags. Fermilab is a very international place. These are the flags of various countries with large groups of scientists at work on experiments here. Below the flags is another control room that you can peer into. This control room is connected by fiber optic connections to CERN, the big accelerator laboratory in Geneva, Switzerland. Scientists in this room monitor CERN's CMS experiment. Scientists from CERN, for their part, collaborate on the DUNE experiment, which is based here at Fermilab. You might have noticed some open stairways that run up the building. Robert Wilson specifically wanted those stairs to have a view of the atrium so that scientists could enjoy getting their exercise while they went about their work. As you look up, you'll see that Wilson's attention to architecture is apparent here too. Every office in the building gets light from either the central atrium or from the outside. This building is meant to be a beautiful and interesting place to work because the scientists and staff are meant to work hard, trying to expand our knowledge of matter, energy, space, and time. In the rest of this presentation, you're going to hear from some of the scientists and engineers about the work that they do at Fermilab. You're going to get a tour of a control room, visit an accelerator, see some particle detectors, learn about telescopes, and hear about the ways that we apply our scientific expertise in the realm of quantum technology. First, though, Valerie Higgins, the Fermilab archivist, will tell you more about the history of the lab.
I'm Valerie Higgins, and I've been Fermilab's lab archivist and historian since 2012. I manage the lab's archives, which hold things like historical records, artifacts, and oral histories. In the early 1960s, US physicists knew the country needed a new particle physics laboratory. Unlike existing particle physics laboratories, the new lab they envisioned would not be associated with any other institution. It would be a place where physicists from any institution could propose experiments and use the accelerators. The Atomic Energy Commission, or AEC, the predecessor to today's Department of Energy, would manage this new lab. The AEC held a nationwide site competition and selected a 6,800-acre area around Weston, Illinois as the site for the new lab, which would be called the National Accelerator Laboratory. You can see here Weston as it appeared shortly after it became part of the lab. In early 1966, the AEC chose physicist Robert Wilson to be the lab's first director. Wilson was director for the Laboratory for Nuclear Studies at Cornell University at the time he was chosen. He had spent much of his childhood in Wyoming, and he brought his love of the idea of the frontier to the new lab, where scientists would explore the frontiers of knowledge. In addition to his skills as a physicist, Wilson was also an avid sculptor and cared deeply about the aesthetics of the lab. To this end, the 11th person he hired was Angela Gonzalez, the lab's artist. Gonzalez designed the lab's iconic logo by combining two kinds of magnets used in particle accelerators. She also created the lab's bold color scheme of oranges, blues, and reds, as well as distinctive posters and publication covers. The lab's first goal was to design and build the world's most powerful particle accelerator. The lab would construct a chain of accelerators that would feed into one another and culminate in a large accelerator called the main ring. Wilson and the chair of the Atomic Energy Commission broke ground on the first part of the lab's accelerator complex, the LINAC, at a snowy ceremony on December 1st, 1968. The lab broke ground on the main ring on October 3rd, 1969. When it was complete, this main ring would be nearly 4 miles around. Once the main ring achieved its design energy of 200 GeV on March 1st, 1972, which you can see lab staff celebrating here, the lab was poised to make new discoveries about the nature of matter and energy under Wilson's leadership. Wilson won the National Medal of Science in 1973 for this work. As the lab pursued its scientific goals, its unique cultural environment also began to take shape. As I mentioned before, Wilson cared deeply about the aesthetics of the lab, and he exerted a great deal of influence on the lab's architecture. He wanted the lab's buildings to be inspiring and to reflect the importance of the work being done there. He had significant input on the design of the Central Laboratory building, which would later be named Wilson Hall in his honor. Shortly after the building was completed, the lab was dedicated as Fermi National Accelerator Laboratory in honor of physicist Enrico Fermi on May 11, 1974. During these early years, the lab also began its prairie restoration program and brought the first bison to the site. Soon after the lab's scientific program got underway, experiment E288 discovered a fundamental particle of matter called the bottom quark in 1977. The lab would go on to build another, even more powerful superconducting accelerator called the Tevatron, which was completed in the 1980s. Several of the lab's scientists won the National Medal of Technology for their work on this project. The Tevatron collided beams of particles called protons and antiprotons, and the lab's experiments CDF and D0 studied the collisions. These experiments discovered another fundamental particle of matter called the top quark in 1995. In 1999, the lab completed a new accelerator called the main injector that you'll hear more about later. During the 1990s and 2000s, the lab also began to expand its research in astrophysics, neutrino physics, and muon physics. You'll learn more about the lab's current accelerators and experiments later in this tour.
Thank you, Valerie, for telling us about the origins of Fermilab. Now we're going to visit some scientists and engineers to learn about the work that they do here at the lab. Our first visit is with Duane Newhart, who works in the accelerator division.
Hi there, my name is Duane Newhart. I've got about 25 years of experience at the laboratory. Most of that was spent running these particle accelerators. The Fermilab has been dedicated to particle physics research for more than 50 years. And we do this by using a series of particle accelerators to deliver a beam of protons to our experiments. The experiments use the beam in different ways depending on what they're studying. In the days of the Tevatron, we would collide a beam of antiprotons and a beam of protons together to enable us to discover things like the top quark, the bottom quark, and the tau neutrino, even search for the Higgs boson. Or we can hit different types of targets with the beam and produce other particles like muons and neutrinos, and be able to study how they interact with their environment. Through the years, both the experiments and even Fermilab's research focus has evolved. But all the particles delivered to our experiments have all come from one place, the Fermilab proton source. Now the proton source is made up of 3 elements. We have our pre-accelerator, which has our 2 ion sources. We have our linear accelerator, and then we have our booster accelerator, which is the first synchrotron in the series. Now the pre-accelerator was updated in 2012 from the original Cockcroft-Walton to its current radio frequency quadrupole form. But in both generations, the pre-accelerators begin with the ion sources. Now I said earlier that we deliver protons to our experiments, but we don't start with protons. We start with neutral hydrogen gas from a gas bottle, actually. But for the hydrogen to be able to move, it needs to have a net charge. So our ion source's function is to make H- ions with a negative net charge. And we do this by injecting the gas into the ion source with a little bit of cesium. And at the right temperature and pressure, we can strike an arc in the ion source. This produces a bunch of electrons. So the neutral hydrogen gas mixes with the extra electrons, and we produce H- ions. So Now we can move them now that they're charged. So we use magnetic fields typically to bend the ions, and we actually use quadrupole fields to focus the ions, also magnetic. But to get the beam to move in one direction, to get it to speed up, we actually have to use an electric field. Now we do this by putting a potential difference across what we call an accelerating gap. And as the ions cross that gap, it picks up the energy. And we typically call this energy electron volts. So in our source, the ions cross the ion source and they leave at 35 kilo electron volts. And then they go into the radio frequency quadrupole, where they gain more energy and they get up to 750,000 electron volts. Now that seems like a lot right now, but they're about to gain 533 times that energy as they pass through the Fermilab LINAC. Now, like the name implies, the LINAC is a straight line. It's pretty simple, but it does use two different types of accelerating technology. The first part of our LINAC is called the drift tube LINAC, and the second part is the side coupled cavity. I don't have time to go into the details about the differences of each, so that's part of your homework, and there's always homework. So in our 500-foot LINAC, there are 647 accelerating gaps, and the H- ions gain more and more energy as they travel. By the end of the LINAC, they've reached 400 million electron volts before they're injected into the booster. As they're injected into the booster, the H- ions pass through a stripping foil. Can't quite see it here, but the stripping foil removes the electrons from our H- ions, leaving only protons in the booster. This is called charge exchange injection. But it allows the booster to accept multiple injections from the LINAC and really build up the proton intensity before it accelerates it. Now I mentioned the booster is a synchrotron accelerator, so it's a circle instead of a straight line. The beam gains energy each time it goes around the booster, and we increase the magnetic field in the magnets to keep the beam moving in a circle. In this case, the beam reaches an energy of 8 billion electron volts, or what we call 8 GeV. That's right before it's extracted out of the machine. So these three elements that we call a Fermilab proton source work together to deliver beam 15 times per second. Now Fermilab continues to evolve. So for our future experiments, we need to have more beam available, and we need to have a higher energy beam, or higher powered beam actually. So we want to increase our beam power for neutrino productions from 700 kilowatts to 1 megawatt at least, maybe to 2. And we're going to do this by building a new replacement for our pre-accelerator on our 400 MeV LINAC. It's called the PIP2 LINAC, and you can see the brand new campus that we've started to create west of the high rise. So this LINAC will reach 800 million electron volts, so it's 800 MeV. It'll use superconducting RF cavities, or accelerating gaps. And the superconducting RF cavities using liquid helium are kept at a very cold temperature, about 2 degrees Kelvin, or minus 455 degrees Fahrenheit. What this does is it reduces the electrical resistance in the cavities so they can add more beam or more energy to the beam over the same amount of distance. This 800 MeV beam will be very densely packed, and it'll allow the booster to be more efficient before it delivers the beam to the downstream machines. Now we have a national and international partners that are helping Fermilab build the PIP2 LINAC. The site construction's already started, and we expect the LINAC to be complete in the mid-2020s. So it's not that far away. There's a lot more information about our new LINAC in the 2 links provided. I hope you have a chance to take a look at it. It's a very interesting machine. So at Fermilab, all the accelerators are controlled from one single location. It's called the main control room. It's tucked in behind Wilson Hall High Rise. Why don't you come visit when you get a chance? Thank you.
Thank you, Duane, for taking us through the acceleration process. Now we're going to follow the beam of particles into the main injector and hear from one of our mechanical engineers, Maurice Ball.
Hi, my name is Maurice Ball, and I'm a mechanical engineer in the Mechanical Support Department of the Accelerator Division. We provide mechanical engineering and technical support to the operations of the various particle accelerators at the laboratory. The main injector is one of those particle accelerators. This building that we're looking at here is one of the buildings that we use to enter and service the main injector enclosure. The main injector is considered the flagship particle accelerator enclosure at Fermilab. So let's take a quick look inside. Welcome to the main injector enclosure, where we are 40 feet underground in a 2-mile circumference ring where elementary particles are being accelerated up to 50,000 times per second around the ring. This enclosure is an interlocked, controlled area due to the hazards associated with particle acceleration. As a result, only qualified trained personnel are permitted to access this enclosure. However, today, using this virtual tour, I'm going to give you exclusive access to this truly amazing machine. But before I do that, let me tell you a little bit about myself and how I began my career at Fermilab. Here's a picture of me when I first started working at the lab. My first engineering project was right here in the main injector enclosure. Before working at Fermilab, I originally grew up in the South. A native of Texas, I received my bachelor's degree from Prairie View A&M University, just outside of Houston, Texas. After that, I completed my master's degree from the University of Wisconsin in Madison with a fellowship from the National Gym Consortium. This fellowship gave me the opportunity to intern at Fermilab. My first job was to design low conductivity water cooling systems for the main injector. These LCW systems keep the critical accelerator components at a precise temperature for prime operating conditions needed for accelerating the beam for the physics experiments. I used the knowledge that I acquired from my high school and college training. Classes such as geometry, algebra, trigonometry, chemistry in high school, and then in fluid mechanics and heat transfer in college, and of course, physics class. These were all used to help me design these systems. In fact, I still use these classes to this very day. One of my first big jobs was to design, specify, and install the secondary manifold piping in the main injector enclosure. So what exactly is the main injector? Well, the main injector is shown right here in this aerial view. It's actually the bottom oval ring in this photo. The particle beam of protons start their journey in the linear accelerator, followed by the booster accelerator beamline. The protons then enter the main injector enclosure, which actually houses 2 accelerator beamlines. From there, the protons are sent to various physics experiments throughout the lab, and even to experiments in other parts of the country. On-site experiments include the external beamlines, the Muon campus, and the Neutrino campus. All of these experiments are on-site here at Fermilab. However, there are off-site experiments also, as far as the state of Minnesota, and soon South Dakota. By the way, I don't want to forget to mention here that Fermilab is known as the premier accelerator-based neutrino research capital of the world. So let's go back into the main injector enclosure for a closer look. Now, as I mentioned earlier, there are actually 2 particle accelerators in the main injector enclosure. One is called the main injector, and the other is called the recycler. These 2 particle accelerators work together to achieve 2 goals for physics experimenters. The first goal is to produce extremely intense particle beams, and the second goal is to accelerate those intense particle beams to extremely high energy levels. Now here in this picture illustration are shown the 2 accelerator beamlines. The recycler ring is shown at the top of the image with the green magnets, and the main injector ring is shown at the bottom with the 2 red and blue magnets. After the particles enter the main injector enclosure from the booster accelerator, they are directed to the recycler ring. The recycler ring uses the permanent magnets, and that's the green boxes shown here at the top, to collect and store the particle beams arriving from the booster, particle accelerator already. And when they enter the recycler, the protons are already at an energy level of 8 billion electron volts. The recycler ring arranges the protons into batches that follow each other around the ring. This batching allows the recycler to collect even more protons to create an even more intense beam. These intense proton beams then enter the main injector, shown in the lower section here, where they are accelerated up to extremely high energy levels, a staggering 120 billion electron volts. The red magnets shown here, also known as quadrupole magnets, have 4 magnetic poles. These poles focus and defocus the proton beam to keep the batch protons together and to keep them from repelling away from each other. The blue magnet shown here is called dipole magnets. They have 2 magnetic poles which steer the protons around the main injector ring, keeping them in the beam tube so that they can be brought back around and accelerated to the higher and higher energy levels with each trip around the ring. There's also other magnets including the octopole magnets, which is the orange tiny device shown here, the sextupole magnets, which is the yellow device, and then there's other magnets that's not shown here, like the trim magnets, the Lambertson magnets, kicker magnets, septum magnets, and permanent magnets. Now, one of the most amazing facts about these magnets is that they can weigh as little as 100 pounds or as much as 20 tons. Now, you can't go to a department store to buy a support stand to support such heavy devices. These support stands are one of the many engineering tasks that has to be designed on site by our resident engineers. Now, as a mechanical engineer, my task is to design fluid systems. Now, as I mentioned earlier, I designed low conductivity water cooling systems for the main injector. Now, in this picture here, you can actually see the piping and the tubing and the hose of various sizes and material makeup. And I use these to deliver and distribute the special water to cool these magnets. Now, if these magnets are not kept cool and at the right precise temperature, they will overheat, resulting in permanent damage to these magnets and quite possibly to the operation of the entire main injector accelerator machine. Now, in addition to the mechanical engineering of the magnets and the cooling water, there's also mechanical engineering of the vacuum systems for the beam tubes and electrical engineering for sending electrical power, controls, and instrumentation to the accelerator equipment. There's even civil and structural engineering for building the 2-mile circumference underground tunnel, which we're currently standing in via this virtual tour. Now, in addition to everything that I've mentioned here and I've talked about so far, I would be completely remiss if I didn't mention one of the most important components of the main injector accelerator: radio frequency cavities, also known as RF cavities. These cavities are critical in that they accelerate or kick the proton particles to higher and higher energy with every trip around the ring. Now, all of the equipment that I've mentioned here, they all work together to manipulate and accelerate the proton beam in a specific manner as the beam propagates around the ring, with some of the particle batches spending an astounding 1.3 seconds duration circling the 2-mile ring before being extracted and sent off to the various physics experiments that I mentioned earlier. In fact, shown here in this next part of the tour is the main injector extraction region. Here, you can see the main injector and recycler beam lines on the left and a new extraction beam line on the right-hand side. This particular extraction beam line receives the extracted beam and then sends it to the neutrino experiments that I mentioned earlier. Now, I've been at the lab for many years, over 25 years, in fact. And even today, I still enjoy designing fluid systems for particle accelerators. However, because of my years of experience in fluid systems, instead of just being just a design engineer, I also now manage projects and the people who design and operate these systems. So as you can see, main injector is truly a flagship of science here at Fermilab, and engineers play a critical role in its design and operations. So thank you for touring the main injector with me. Now, on to neutrinos.
Thank you, Maurice, for that underground tour. And as Maurice says, now on to neutrinos. So we're going to meet Anne Norrick, who will tell us about the elusive neutrino and some upcoming experiments at the lab.
Hi everyone, my name is Anne Norrick and I'm a postdoc here at Fermilab working in experimental neutrino physics. I'm so excited to be able to tell you a little bit about neutrinos and how we study them here at Fermilab. Neutrinos are, in my opinion, the coolest particle around. They are the smallest known massive particle and the second most abundant particle in the universe. Even though they're incredibly abundant, they're very hard to see. They interact only through something called the weak nuclear force, which, as the name suggests, is quite weak. That means that interactions between neutrinos and anything else are quite rare. In fact, they can travel through a light year of lead without stopping. In order to see enough of them for us to say anything definitive, we have to build very large detectors and very intense beams of neutrinos. Neutrinos were first theorized to explain a puzzle in radioactivity back in 1930. Nowadays, we know that neutrinos are part of all nuclear reactions. They're created in the nuclear fission in stars and in supernovae, as well as from the decay of unstable particles created in high energy collisions in the atmosphere and in man-made nuclear reactors. But here at Fermilab, we use our accelerator complex that you've heard a bit about to make beams of neutrinos. We take the fast-moving protons from the accelerator and we smash them into a solid target. Mostly these collisions make a particle called a pion, which is a short-lived particle that can be positively or negatively charged. We then use strong magnetic fields to select one charge of pions. The pions don't live for very long though. They decay into a charged particle and a neutrino. Then the charged particles get absorbed by the rock and the neutrinos just keep traveling right through the Earth to our detectors and beyond. So if neutrinos can go right through everything, how do we see them? Well, technically we don't. We only ever see the charged particles that are created when a neutrino interacts with the atoms in our detectors. The neutrino enters our detector unseen, interacts with the nucleus in the detector, and charged particles are created. These charged particles come flying out and they leave traces in our detector. We can then use algorithms to take the traces left in our detector and reconstruct what particles left those traces. Reconstructing those particles is important because it tells us about what type of neutrino we had. We know of 3 types of neutrinos called flavors that each have a charged buddy: electron neutrinos, muon neutrinos, and tau neutrinos. For one type of interaction, a neutrino will interact and its charged buddy will come out. So an electron neutrino interacts and an electron is produced. A muon neutrino will produce a muon, etc. It is important to know what type of neutrino you have because neutrinos do something really funny where you can be holding onto an electron neutrino, and if you were to toss it across the room, it could be a muon or tau neutrino by the time it interacts. This is a process called neutrino oscillation and is a quantum mechanical consequence of neutrinos both having mass and the fact that the masses of the 3 different neutrinos are different from each other. Studying this process in both neutrinos and their antiparticles, antineutrinos, could help explain how the universe was created. If matter and antimatter were really exact opposites of each other, the Big Bang would have just collapsed back on itself and the universe as we know it would never have existed. The differences between matter and antimatter are called charge parity violation. And it is one of the things we are trying to understand using neutrinos by studying the way they change over very long distances. To do that, we often have 2 detectors, one close to the source of the beam and one farther away, so the neutrinos can change flavor by the time they get there. The experiment that I work on is called NOVA, and we have one smaller detector here at Fermilab, 100 meters underground, and a 14 kiloton detector up in northern Minnesota. This is the surface building for our underground experiments. Everything we have underground was brought down using large cranes. We take large sections of the detector and can bring them down using the crane and the shaft. You can look down the shaft, but it makes me a bit dizzy, so I generally avoid looking directly down. Underground, we have a large cavern originally dug out for the MINOS experiment. One of the nice things about a neutrino beam is that we don't have to have a pipe to carry the beam since neutrinos travel right through everything. So the spot where the beam enters the underground hall is right up where you see the little red circle. The NOVA near detector sits in its own side cavern, slightly to the side of the beam, because that lets it see neutrinos of only one specific energy. The NOVA detector is made of extra strong PVC cells, a lot like a giant network of pipes. The cells are arranged in layers, with one layer going up and down and the next layer going side to side. Each cell is filled with clear mineral oil, think of baby oil, and a special substance called a scintillator. When a charged particle passes through a scintillator, the scintillator releases light. We can then catch that light and measure the level, which gives us information about where the charged particle was in the detector and how much energy the particle had at that point. Here at the back of the detector, we have a small section called the Muon catcher that includes some heavy steel to help muons within the detector stop so that we can better measure them. The Nova Far detector sits on the surface of the Earth, which has some challenges because there are actually charged particles raining down on us all the time, and our Far detector sees that. This is real data from the Nova Far detector. We can take advantage of the fact that the neutrinos from our accelerator are sent for only 10 microseconds every 1.3 seconds, so most of the activity gets cut out just by looking at the timing. Then we can use spatial and timing grouping algorithms to pull out individual interactions in the detector. That allows us to drill down until we have one and only one neutrino interaction to study. One way to make this problem easier is to put our very large detectors very far underground, so the Earth can act as a shield against these particles entering our detector. We've done this previously with the Minos experiment, whose far detector was in northern Minnesota, and we're looking forward to doing this again with the Dune experiment. Dune is a new long baseline neutrino experiment that is currently under construction and should begin taking data in the near future. It will use truly giant detectors filled with ultra-cold liquid argon, with the near detector here at Fermilab and the far detector deep underground at the Homestake mine in western South Dakota. The Dune detector actually works by detecting free charges created when the particles pass through the argon. For this experiment, we have to build a whole new beam line to send the ultra-intense beam out to South Dakota and to build new detector halls here on site. Dune will allow us to make precise measurements of possible charge parity violation in neutrinos. This new detector design, as well as the longer baseline, opens up new opportunities for better measurements than were ever possible before. We're also going to have a very capable near detector complex that can make additional measurements of how neutrinos interact with the large and complicated nucleus. That is the physics that I'm most interested in, and I could happily talk about it all day, but unfortunately I'm running out of time. But Dune is certainly exciting and should provide deeper insights into neutrinos and their place in the universe. I hope you enjoyed hearing a bit about what we do here with neutrinos at Fermilab and that you'll come for a visit sometime. Thanks.
Thank you, Anne. In addition to neutrinos, physicists here are studying a fundamental particle called the muon. Let's meet Brendan Casey, a physicist here, who will explain the G-2 experiment and then take us out to the Muon campus.
So let's talk about what we're trying to measure with the Muon G-2 experiment. We're trying to measure the magnetic strength of the muon, which we call G. For elementary particles like the muon, G equals 2. Since we're trying to measure the muon's magnetic strength, we could think of it like a bar magnet with a north and south pole. Now, if you want to measure a magnet's strength, the best thing to do is use a different magnet that you know very well. If we put a muon in a strong magnet, it's going to spin around very fast. But if we put a muon in a weak magnet, it's going to spin much slower. So if we know the strength of our magnet and we can measure how fast the muon is spinning, we can get the value of G. We call the spinning motion precession. So we have our muon in our magnet and it's spinning. Let's see what happens if we add more elementary particles. The muon sees the magnetic field from them and it slows down. Now, what's really happening on our experiment is these are all virtual particles that constantly pop in and out of existence following the rules of Heisenberg's uncertainty principle. We can't see the particles, but the muons can. And so the takeaway message is virtual particles always shield the magnetic field the muon sees and make G greater than 2. So let's now see how these virtual particles affect the value of G. Like we said before, for elementary particles, G is equal to 2. Now if you add virtual electrons and photons, G increases slightly to 2.002331. If you add in virtual quarks and gluons, it gets slightly bigger. And if you add in virtual W and Z bosons, Higgs bosons, and neutrinos, it gets ever so slightly bigger. Let's take a look at the measured value. That value is 2.00233181. So the last two digits are wrong, which is possibly an indication that there is a new elementary particles that are affecting G and shielding us in the magnet that we haven't discovered yet. So the goal of our experiment is to measure these last two terms with 4 times greater precision than the previous measurement, and that'll tell us if there are new particles or if we just messed up the experiment. Now, we only care about the virtual contributions, we don't care about the 2, and we usually subtract that off, which is why we call the experiment G-2. Hello, my name is Brendan Casey, and I am a physicist at Fermilab who works on the Muon G-2 experiment. And I'm going to give you a little tour of that experiment if I can figure out how to work my camera. Okay, so the first thing you see when you come to G-2 is this big silo looking thing here. That's our liquid nitrogen tank. And that's actually, we go through a lot of liquid nitrogen here. It's our second most expensive thing that we have. The most expensive thing we have is our people, because they're our most precious thing. Okay, let's go inside. Okay, we're inside now, so let's see what we can see. So the first thing you see when you come in is the flags of all the countries that collaborate on Muon G-2. There's all our countries there. And this is our control room. What you see here is our computer room. So it's not that big, but we've got all our computers here where this is our control system, our clock. And then we've just got a little computer bank here, which reads out all the data from the hall, comes in. Okay. Nice little computer room. We read things out with GPUs. That's kind of cool. You know what that is? Those were made for people making video games. Okay, so we're going to come inside now. Welcome to the G-2 hall. Okay, the first thing we're going to do is turn off that fan so you guys can hear me. So let's hit the north fan button. Okay, that's a little bit better. So what you see when you come in is some of the pictures of little introductions to different people that work on G-2, where they're from, what they like, what they work on. You know, we won't go to everybody, except there's a really good looking picture here. So I just wanted to make sure to show you that. Okay, so here's the ring. What you see over there in that back corner is that's where the muons come in. Okay, they come into our ring. And I'm trying to get the whole ring in here. I guess if I turn sideways I can. Alright, so this is the G-2 ring. What you see in white is actually a blanket. Okay, because, you know, when the temperature changes by a couple of degrees, our magnet opens up and closes just a tiny bit, and that's actually one of the biggest problems we have. So that's why we have those fans here. What they're doing is blowing the air in a circle, so it goes around the ring, and that's how we keep the airflow, we keep the ring all the same. Okay, you see a bunch of power supplies down there. Okay, see over there, that's where the cables are going up into the computer room where we just were. Okay, we can walk down here. What you see down there is that's our laser hut. You can see all the cables going out to the different parts around the ring. Okay, that little green blinking light there that's a radiation monitor. That will turn everything off, turn the beam off if for some reason we have too much radiation. But we really, muons, you don't get a lot of, we have fairly low intensity muon beams, so that's not really a problem for us. Okay, so let's take a look around outside what we have. Okay, this is our kicker corner. This is, the kicker kicks the muons onto orbit when we inject them. Okay, so that's really important. What you see is these big long pipes on the back of the wall, that's actually what makes the kicker, what makes the kicker pulse. And those are kind of neat. They're triaxial cables instead of coaxial cables like you usually see. Okay. We have a little cryogenics plant back here. That's where we bring all our those are the kicker cables. Okay, and this is our cryo. That's our big doer up there. We come around. Here's our cryo going into an inflector magnet, which is a magnet that cancels the main ring magnet so that the muons could come in. Here's our beam line of the muons, where the muons come in. So they just come in, and then there's a hole over here. And that hole goes all the way through. And that's how we get the muons into the ring. Okay, I'm gonna come back, I'm gonna pause this and come back around. Okay, while I'm down here, I'm just gonna check the flow on some of my tracker modules, because that's one of my jobs. That's our, this is our filter system for our gas. We don't want bad things coming in. Okay, it's the other side of the beam line. And then I'm gonna pause this and go upstairs and then come down into the ring. Okay, so we're gonna come down the stairs. These are power supplies for the quadrupoles that keep the muons stored. So the muons come in right back there, okay? They're on the inside. We have vacuum pumps. These are turbo pumps. They're called turbo pumps because they look like a turbo on a jet plane. These are feed-throughs for the quadrupoles. This is the interconnect system, which is where we connect the different parts of the ring. What you see in these black things are calorimeters, so those are on sleds, so we could move them in and out. There are 24 of those going around the ring. Here's where the kicker goes into the ring. Those big things there, we call them bazookas because they look like bazookas, and that's just a cool name. Here's some more stuff. So come over here. These are fiber harps there against the wall. This here is our trolley drive. We have a trolley that goes all the way around the ring. So this is what controls that and pulls it around. It's actually a cable car instead of a trolley, but that's okay. We just call it the trolley. Here's the tracker. This is where that flammable gas was going. Maybe you could see the lights blinking. That means it's working, which is very good. A couple of weeks ago, we had to spend a whole week getting that working again. That was very stressful, but in the end of the day, we got it working. Here's some of our readout for the tracker. More power supplies. This is over here where our trolley lives. That back there, that's the trolley garage. So a lot of cool things down here. And if I had about an hour, I could explain it all to you. Hello, everybody. This is Brendan Casey back again. It's Tuesday morning. What you are looking at here is what we call the wiggle plot. This is data that we're taking in real time. So I'm going to clear this. So while I explain it to you, you can watch it accumulate in real time. So let's talk about the way that we actually measure the muon precession frequency. We can't really see the muons precess, but what we can see is what happens when they decay. So muons decay into, these are positive muons, so they decay into positrons and neutrinos, and the positron likes to go in the same direction as the muon spin vector. So what we can do is put detectors on the inside of our ring called calorimeters that I showed you in the video. And there's going to be times when a lot of positrons hit those calorimeters, and that's when the muon is pointing at the calorimeters. And there's times when there's not going to be a lot of positrons hitting the calorimeters, and that's when the muons are pointing away from the calorimeters. So by counting positrons versus time, we know when the muon is pointing towards us and when the muon is pointing away from us, which is telling us how fast it's spinning. So we fit this, and the time between the peaks is what gives us the precession frequency. So you could see in just the few minutes it took me to explain that to you, you can see the data accumulating in real time in one of our calorimeters. We have 24 calorimeters, so in real time, it's actually 24 times this. And you could see the data is coming in pretty quickly. It's a lot of data. It's a lot for us to handle. A lot of times we're completely swamped in the data that we have coming out of this experiment. So all we have to do now is take data like this for a few years. It would be great if we just sat back and everything worked, but as you saw, things do go wrong and we have to go in and fix them. But after we've ran for a few years, we're probably going to run for a few years more. And that's going to give us all the data we need to make the world's best measurement of the G factor of the muon. Thank you very much.
Thank you, Brendan, for these insights into the tools of muon studies. It's especially exciting to see real data coming in from your experiment. Next, we're going to learn about monitoring detectors in our control rooms. Our speakers will be Harry Ferguson, who oversees the Rock West control room in Wilson Hall, and Matt Judah, who is the shifter on duty today.
Hi, my name is Harry Ferguson. I manage Rock West at Fermilab. Let's go on a virtual tour. Welcome to the Remote Operations Center at Fermilab. Fermilab has two what we call ROCs. The ROCs, or Remote Operations Centers, basically provide a space with equipment where remote experiments from around the world are operated and monitored. Additionally, the ROCs can connect to 33 remote ROCs from Minnesota to as far away as Russia, Brazil, or the United Kingdom. ROC East, located on the east side of Wilson Hall, is associated with the CMS experiment at CERN's Large Hadron Collider, located in Central Europe. While ROC West, located on the west side of Wilson Hall, is associated with 6 experiments using the world's most powerful 700 kilowatt proton beam to study one of the universe's most abundant particles, the neutrino. Over the last 6 years, 6 experiments studying neutrino interactions and supporting the development of next-generation neutrino detectors have been operated from Rock West. These include NOVA, Microboon, 35-ton, Annie, NOVA Test Beam, and until last year, Minerva. Recently, Icarus has established a console in Rock West as the experiment's installation is completed and early commissioning begins. Rock West also hosts 2 to 3 days a month the Dark Energy Survey, a visible and near-infrared survey of the universe and the growth of large-scale structures. Rock West is in operation 24/7 with an average uptime, that is, experiments operating and actively collecting data, of 97.8%. Rock West relies on the main control room at Fermilab to supply the 700 kilowatt proton beam, which produces the neutrinos used for study. The individuals that operate the experiments are called shifters, and they collaborate with the main control room to understand schedules and status of the supplied beams. Here is Matt, who will give a brief description of the operation from a shifter's perspective.
So I'm going to talk to you a bit about what the responsibilities of shifters are in the NOVA experiment. So our shifters are really responsible for, are we taking good data? It's the question they want to answer throughout their entire shift, which ends up being about an 8-hour period of time that happens 3 times a day for the different periods that we're interested in for our detector. So the shifters, because they're concerned with, are we taking good data, they look at each individual event as it happens in our detector, where an event is an individual, like basically a picture taken of the detector at a certain moment in time. We add up all of these events to take a bunch of data and study things for all of the physical processes that we're actually interested in as the NOVA experiment, in particular neutrino interactions. Throughout your shift, you end up collecting about a terabyte of data, which in terms of the laptop I'm using, that's equivalent about to 4 MacBook Pros, if anyone's interested in how much data this is on every shift that we take. We take our shifts 24 hours a day, with 3 shifters taking 8-hour periods of shift. And these shifters can be anywhere in the world. We have, I think at the moment, 32 remote operating control rooms that are able to access our detectors and all the information associated with our detectors to make sure that we are taking good data. So how does one ensure that we are taking good data? Well, first, this basically comes down to, is the detector entirely synchronized across all of our electronics channels? Because the NOVA detector is made up of about 350,000 channels, this is actually a really big to-do. So to do this, we look at several different pieces of information. The first would be the event display. And so this shows the pictures of our detector at certain moments in time that we think are interesting. And you can look at the event display and see the charged trajectories of charged particles as they pass through our detector. And so if any of these, if tracks are missing segments or certain parts of the detector aren't being read out, it's readily identifiable on the event display. And so you would know something was going wrong within the experiment itself. And so we would have to do something about that. Other ways you could tell about this is to ask the question, are we writing out any of the data that we're taking? If you look at some of the NOVA screens, you'll see a box that has a bunch of just incrementing numbers. Basically, this tells us how many triggers or certain pictures that we're interested in from the NOVA detector, how many of these are being saved for how many we're sending out. And so as you watch these numbers increase, you'll hopefully see that we are writing out all of the information that we are interested in writing out to begin with. So the typical problems that people can run into while operating the experiment are things like the detector crashing, which basically can happen anytime different components of the detector become out of time with each other, or certain machines, computers that are being read out crash or need to reboot. Things like that can cause problems within the experiment, and would typically require us to ask one of our expert operators to work on these problems and get the detector back in the running condition. The one thing that I think is really important to mention about the shifts is that shifters play an extremely important role in the experiment. They offer our first line of defense in making sure that all of the data we take is good, and they can interact with the detector in a way that you don't after all of the data is taken. So you're really important in making sure that the data we analyze for all of our physics results is good all the way through our experiment.
Thanks, Matt. It takes many run coordinators and shifters like Matt at Fermilab and from all over the world to run the various experiments. Without shifters, the data that leads to discovery would not exist. Shifters also serve a vital role of explaining the science behind all the experiments here at Fermilab to our visitors. The ROCKS environment also provides a collaborative space for the physicists to discuss and resolve problems and find innovative solutions. Not surprisingly, ROC West has hosted over 30,000 visitors since its opening, which ranged from students to the general public to heads of state, to an original member of the Monkees, who visited in 1970. ROC West provides the perfect environment for direct interaction between the visitors and the physicists doing the research. Let's summarize. The world's most abundant particle, neutrinos, are being investigated through a worldwide connection and collaboration of international physicists in our remote operating centers. Thanks for visiting.
Thank you, Harry and Matt. Next, we're going to learn about computing and quantum science from physicist Adam Lyon.
Hi, I'm Adam Lyon, and I'm a particle physicist and senior scientist here at Fermilab. I have several roles here at the laboratory. For one, I'm the Associate Division Head for Science for the Scientific Computing Division. The Fermilab Scientific Computing Division has many scientists working on nearly every experiment at Fermilab. It's my job to make sure they have time to work on science along with their computing. I also work on the Muon G-2 experiment, which is also on this tour, so be sure to check that out. And I do research in quantum computing, which is research in a new type of computer. Regular computing, of course, plays a huge role at the lab. We use computers to record and store enormous amounts of data from the experiments located here at the lab and elsewhere. Computers process that data for easier analysis by physicists, and we use computers and networks to distribute that data all around the US and the world, enabling experiments with hundreds or thousands of collaborators to have all of their scientists producing results and discoveries. Behind me is a picture of the Feynman Computing Center with the Wilson Hall high-rise in the background. Much of our important computing infrastructure is in this interesting-looking semicircular building. We have powerful computing resources here at Fermilab. And here's a picture of the inside of one of our computer rooms, and you see racks and racks and racks of computers, and we have rows and rows and rows of these things. And here's a picture of a Fermilab employee maintaining these machines. We also use computers all over the world, and we even use enormous supercomputers at other national laboratories in the US. We also do research and development on how to make our computer codes easier to write and more efficient, and how to use the wide variety of available computing resources more effectively. About 2 years ago, I started working in an area called quantum computing. And in fact, in 2019, the laboratory inaugurated the Fermilab Quantum Institute. Quantum computing involves using quantum mechanics directly for making computations. Quantum mechanics dictates how very small things like atoms and particles work, and it's very unlike our everyday world that we experience. For example, in quantum mechanics, results are governed by probabilities and are not deterministic. Systems can be in a combination of states until you measure them, and particles can tunnel through barriers. While designing and fabricating modern electronics, like what's in your cell phone or computer, rely on an understanding of quantum mechanics, those devices don't use quantum in their computations. We are now trying to build computers that do use and exploit the principles of quantum mechanics in computations themselves. In the past few years, the technology to build devices that behave like artificial atoms, that is, behave using the strange rules of quantum mechanics, has advanced dramatically. This technology is still in its infancy, but we are learning how to use it to simulate nature more effectively than even the largest supercomputers. Fermilab has many connections to this field that are pushing our interest in quantum computing. Very special devices that we are world experts in building, called superconducting radio frequency cavities, that are used in our particle colliders to accelerate particles to nearly the speed of light, and one of these is shown here, are directly related to cavities that we can build to make quantum computing devices. So here's a quantum computing device that we're trying to build, and you can see things that kind of look like those cavities hanging vertically in the device. And here is a fancier picture of that device. So we're trying to build our own quantum computer made from these cavities. We're also developing the technology of quantum sensors, which are devices that can detect and perhaps discover particles with unrivaled sensitivity. This is a device here that's looking for particles of dark matter. Many quantum computers need to be kept very, very cold, just a few thousandths of a degree above absolute zero. Fermilab engineers are experts in designing and building electronics that work in this very, very harsh environment. And here is such an engineer working in that area. Just as quantum computers are very different from traditional computers, a quantum internet would also look very different, and Fermilab is very active in that research. Here's a picture of scientists at one of the endpoints of a prototype quantum network here at Fermilab. We also have researchers, myself included, working on algorithms that will be useful for particle physics, as well as simulating future quantum devices with traditional computers. Finally, this past summer, the US Department of Energy awarded 5 national quantum centers, and Fermilab is one of them. Our superconducting quantum materials and systems center will spend the next 5 years building and researching our cavity-based computer, as well as exploring algorithms and applications that will exploit its unusual capabilities. You can see that computing is an integral part of Fermilab in the sense of collecting, processing, and analyzing data from experiments with traditional computers, as well as cutting-edge research in traditional computing and this exciting emerging field of quantum computing.
Thank you, Adam. Our next speaker is engineering physicist Donna Kubik, who's going to take us deep into the cosmos and tell us about building tools for astrophysics and cosmology.
Hello, here I am working in the lab on a microwave electronics circuit. As an engineering physicist at Fermilab, I'm thankful and thrilled to have the opportunity to work both in the lab and in the field on cosmic physics projects. In addition, I often have the opportunity to share my enthusiasm with visitors. Here I am with 2 colleagues waiting for a tour group to arrive. Today, you are my tour group, and I'd like to tell you about the Fermilab Cosmic Physics Center. Cosmic physics is the study of the laws and contents of the universe. We use the distribution of matter and light throughout space as a gigantic laboratory. First, I'd like to introduce you to 2 projects that study the mysterious dark energy that is accelerating the expansion of the universe. The Dark Energy Camera on Cerro Tololo in Chile, and the Dark Energy Spectroscopic Instrument on Kitt Peak in Arizona. The sensors are the eyes of the telescope. The Dark Energy Camera sensors were designed and fabricated by Lawrence Berkeley National Lab and then assembled, tested, and commissioned at Fermilab by people from across the international collaboration. The camera is comprised of 74 optical sensors. The camera creates digital images of distant galaxies that probe nearly halfway back to the Big Bang. Cerro Tololo is a great place for an optical telescope. The high elevation and proximity to the calm air mass rising over the Andes from the Pacific Ocean is essential to minimize atmospheric distortion, which can degrade image quality. The goal is to map hundreds of millions of galaxies and detect thousands of supernovae to find patterns of cosmic structure that will reveal the nature of dark energy. The Dark Energy Spectroscopic Instrument on Kitt Peak will pinpoint the location and velocity of 35 million galaxies by pointing an optical fiber at each galaxy. The high-precision 3D map will give us new clues about dark energy. Strong evidence suggests invisible dark matter comprises most of the matter in the universe. Super CDMS, Sensei, and ADMX are searching for the identity of dark matter. Unlike telescopes that benefit from high altitudes, many dark matter experiments benefit from being deep underground, shielded from cosmic rays and other background radiation, in laboratories like SNOLAB in Sudbury, Ontario. In fact, SNOLAB is as far below sea level as the telescopes are above sea level. Super CDMS and Sensei will be located in a clean room deep underground in SNOLAB. Super CDMS sensors, made of germanium and silicon, are used to search for interactions of weakly interacting massive particles that may constitute the dark matter observed in the universe. Sensei scientists are using innovative sensors called skipper CCDs to search for the lightest dark matter particles anyone has ever looked for. The skipper CCDs are also useful in the field of quantum optics. Using a large magnet, a microwave cavity, and ultra-sensitive low-noise quantum electronics, ADMX is testing the theory that galactic dark matter halos could be made of particles called axions. Now, I'd like to introduce you to the South Pole Telescope. Light from the first moments after the Big Bang is still traveling across the universe. This light is called the cosmic microwave background. And we've built a camera that is sensitive enough to detect it. The camera is comprised of 2,700 antennas searching for the faint microwave signals that can tell us about the physics behind the Big Bang. We installed the camera on the telescope, which is just a short walk from the South Pole. This is me at the South Pole. The South Pole is a great place for a microwave telescope. Located 2,800 meters above sea level, it is very high and dry and cold. These conditions are optimal because water absorbs microwaves. At the South Pole, it is so cold that moisture in the atmosphere freezes out, providing an unobstructed path for the microwaves, which have been traveling for nearly 14 billion years to reach the telescope. The telescope continues to scan the cosmic microwave background 24/7. Thank you.
Thank you, Donna, for telling us about these amazing scientific instruments. Now it's time to learn about applications of our research through the Illinois Accelerator Research Center. Our host will be Michael Geelhoed, an engineering physicist at the lab.
My name is Michael Geelhoed, and I'm an engineering physicist here at IARC at Fermilab. Here, scientists and engineers work side by side with industrial partners to research and develop breakthroughs in accelerator technology and translate them into applications for the nation's health, wealth, and security. Looking inside, we are in our Accelerator Applications Development and Demonstration Tool, better known as A2D2. A2D2 delivers high energy electrons for radiation-driven chemistry for samples placed in the machine. Here was red food dye. The high energy electrons are breaking down these complex molecular structures to their simpler compounds. As we start to zoom in, you'll start to see the red food dye disappear as small pixelations appear on the screen. Now, those small pixelations are actually X-rays. Those X-rays are being generated by the electrons coming from the top, bombarding the water, and then creating X-rays that the camera is picking up. In that process, it's delivering radiation to the water, breaking down those chemicals. The results are shown here after approximately 10 kilograms of radiation. It's pretty easy to determine which one's the before and which one's the after. But from these applications, from water treatment to medical device sterilization, our Fermilab scientists and engineers are once again partnering with industry and academia to create the next generation of industrial accelerators. Generally speaking, those accelerators are made out of copper. However, shown here is our digital concept of a cryogen-free, compact, superconducting particle accelerator, combining electron gun technology and conduction cooling with a little bit of advanced superconductive cavity coating techniques and a few more technologies. Our accelerator will be able to provide the beam power for those particular applications. Stay tuned.
Thank you, Mike, for that tour of IARC. So now you've had a glimpse of the cutting edge research that we do at Fermilab. For more videos, you can click on the link below. And for more information about the experiments and our history, you can go to our webpage. Finally, we hope that you will visit the lab in person sometime. There are always new developments and new experiments, and we love sharing the beautiful site and the amazing science with the public. Thank you for joining us today.